for a few moments as I outline the emergency procedures to be followed at today's event. This building is equipped with a fire alarm system, and in the event of an emergency, the alarm will sound. Please note that we have no planned drills for today, so if the alarm sounds, we will treat it as an indication of a real emergency. Once the alarm has sounded, calmly make your way through one of the exits. This auditorium has 4 exits directly to the back and 2 emergency exits at the front of the auditorium to the left and right. Once outside the building, make your way to the assembly area, which is to the north of the building. Stay at the assembly area where you will receive further directions from university personnel. In the event of an earthquake, stay calm. There are no tables under which we can cover and hold, but you must beware of falling debris. Once the shaking stops, exit the building in a calm and orderly manner and assemble at the assembly area where you will receive further instructions from a university personnel. Thank you.
Good evening. Professor Indar Ramnarayan, Deputy Principal, and other members of the campus executive management team, the University of the West Indies St. Augustine campus, our distinguished speaker, Professor Krishpersad Manohar, deans, heads, faculty, staff, and students of the UWI St. Augustine campus, specially invited guests, members of the media, ladies and gentlemen, good evening and welcome to all. I am Professor Shirin Hack, Chair of the Open Lectures Committee here at the UWI St. Augustine campus, and it is my great pleasure to welcome you this evening to the professorial inaugural lecture featuring Professor Krishpersad Manohar from the Faculty of Engineering at the UWI St. Augustine campus. It promises to be an evening of celebration of intellectual thought and innovation. This has been my first year as chair of the committee, and I've been loving it, to be part of one of the things the universities do best, the research where new knowledge is created with the aim of making this world a better place. The amazing woman of science, Rosalind Franklin, said, "Science and everyday life cannot and should not be separated." There is no better example of that than the feature lecture this evening by Professor Krishpersad Manohar on his journey to net zero insulation for sustainability. The role of the Open Lectures Committee is to advance the university's knowledge transfer agenda via high-quality lectures by exceptional local, regional, and international speakers. These lectures are just one of the platforms that our campus uses to engage the wider national community on issues relevant to local and regional development, impact regional policy making, analysis and evaluation, and of course, stimulate and encourage the pursuit of excellence and scholarship, an example of which we will see this evening. Apart from the distinguished open lecture series, the committee also hosts professorial inaugural lectures to showcase the research of the campus's recently appointed or promoted professors. This evening is just about that. Be sure to follow the UWI St. Augustine Facebook page, where you will see information on upcoming events for the next academic year with another packed schedule. At this point, I would like to invite Professor Indar Ramnarayan, Deputy Principal of UWI St. Augustine campus, to deliver opening remarks. Let us welcome him to the stage.
Thank you very much, Chair. Our distinguished speaker, Professor Krishpersad Manohar, Professor Bisham Ramlal, Dean, Faculty of Engineering, other deans, directors, deputy deans, heads of departments, relatives and friends of Professor Manohar, faculty, staff, and students of the UWI St. Augustine campus, ladies and gentlemen, good evening, everyone. It is my privilege to welcome you to Professor Krishpersad Manohar's professorial inaugural lecture titled The Journey to Net Zero, Insulation for Sustainability. Thank you to the Open Lecture Committee for arranging these lectures, which serve as a platform for this campus's new professors. It is fitting public acknowledgement to have professors share the work that is so passionately pursued over their careers. These lectures provide the opportunity for the campus community to gather, not only to celebrate and esteem academic accomplishments, but also to learn from the professors' vast knowledge and experience. This evening, we are privileged to have Professor Manohar, who is credited with several impactful and widely cited scholarly works, deliver the lecture. Professor Manohar, I extend my heartfelt congratulations on this well-deserved appointment to the rank of professor. Congratulations. This is the highest rank that anyone could achieve in the academic world, so well done. It's not easy to achieve. Some people do achieve it, and congratulations to all of those who have reached or who have earned that title. Your outstanding body of applied and experimental work in energy and thermofluid mechanical engineering, extensive published research, and your invaluable contribution to our institution have earned you this title. It has also earned the respect and admiration of colleagues and students alike. Thank you for your distinguished work. I wish you much success as you continue to contribute to the advancement of knowledge in your discipline. As the region's premier tertiary education institution, the UWI continues to emphasize the importance of our academics producing scholarship, research, and innovative solutions relevant to the Caribbean context. Indeed, Professor Manohar has embraced this vision in his academic journey. His commitment to the Caribbean is also evident this evening, as his lecture will address a very important issue for our region, reducing carbon emissions. I am especially eager to listen to this presentation on thermal insulation as a means of reducing carbon emissions in Trinidad and Tobago. I am eager in part because as chair of the Campus Environmental Committee, I am always interested to learn about sustainable, environmentally friendly solutions that can reduce our carbon footprint. I am also eager to hear Professor Manohar's lecture, as I believe that building insulation as a means of energy-efficient cooling in a high heat and humid climate is not at the forefront of the average Caribbean citizen's mind. In fact, I never realized that this could be a strategy. So imagine a region where we can rely less on air conditioning units for cooling comfort and save on electricity costs. And as we all know, that is about to increase fairly soon, while reducing carbon emissions. Enhanced energy efficiency within our built environment is necessary if we are to secure a more sustainable and environmentally conscious future. Professor Manohar, I look forward to an intellectual exploration and thought-provoking session. I'm optimistic that this lecture can help to propel policymakers to make informed decisions and institute measures to enhance energy efficiency in the Caribbean building design and construction. As I close, I say thanks to you, colleagues, students, and esteemed guests for supporting this lecture series. I'm pleased to see many of you have demonstrated genuine interest in this area. I urge all of you to actively engage in the lecture and take full advantage of this opportunity to expand your horizons. Please enjoy the lecture. Thank you very much.
Thank you, Professor Ramnarayan, for those wonderful remarks which has set the lovely stage for what's coming up very shortly, the feature presentation. I would now like to invite Professor Bhisham Ramlal, the Dean of the Faculty of Engineering, to introduce our feature speaker, Professor Krishpersad Manohar. Let us welcome him to the stage.
Thank you, Professor Shirin Haq, Chair, Open Lectures Committee, Professor Indar Ramnarayan, Deputy Campus Principal, and other members of the Campus Executive Management Team, our distinguished speaker, Professor Krishpersad Manohar, deans, heads, faculty, staff, students, specially invited guests, relatives especially as well, members of the media, ladies and gentlemen, good evening again. I will speak to Professor Manohar's journey at the UWI while he speaks about the journey to net zero. So let me tell you a little bit about Professor Manohar. He is a long-standing member of the UWI and the Faculty of Engineering. He completed both his BSc and PhD in Mechanical Engineering at the Faculty of Engineering here at UWI. And so he is really a product out of the Faculty of Engineering and certainly the UWI. He completed his bachelor's degree in 1986. After graduation, like most of our engineering graduates, they head out to industry to gain employment. And he was no exception. He joined in his first employment, he joined Anadril Schlumberger, where he worked for a while, and then he went off to Halliburton. There again worked for a while, and then he was plant engineer at Industrial Bags Limited for a while, and then joined as a project engineer Amoco Trinidad Oil Company. But I think the calling was there already, because after that he served as a lecturer at the San Fernando Technical Institute for 2 years. And so we kind of get an indication of where Professor Manohar will come to. He joined UWI in 1995 as an assistant lecturer, promoted to lecturer in 2000, and senior lecturer in 2009. He achieved promotion to professorship in May 2022. So, you know, it's a while, this lecture is a while in coming, so I'm very pleased that he's able to do it. In terms of his university service, Professor Manohar has served at various levels of the institution. He has served as, acted as a head of department, and recently served as a deputy dean responsible for facilities management. He also, of course, in the many years he's been here, has extensive teaching experience. He was elected as the department's most outstanding lecturer in 2015. That is no small achievement, given the nature of the particular discipline he's in. He has supervised several graduate students, including several PhDs, MPhils, and Masters of Science theses. And at the undergraduate level, he has supervised over 160 final year projects. And again, that reflects the type of person he is in terms of contributing to his department and to the UWI. He actually received the UWI NGC Outstanding Research Mentorship Award in 2012. So he's not only a good teacher, he's also a good researcher. Professor Manohar has made significant contributions to the profession, to public service, and of course, to community. I'll give you a few examples. You know, his resume is long, and I don't want to make it sound, extended, so I will just give you a sample of some of the wonderful things he's been able to achieve over the many years he has served us and served us well. He's a member of the American Society of Heating, Refrigerating, and Air Conditioning Engineers CARICOM chapter, and was instrumental in forming the, as it's called, ASRE CARICOM student chapter here at UWI St. Augustine. He's a member of the editorial board of the International Journal, of Mechanical Engineering, and serves on several other, as a reviewer for several other journals. For example, he has served on the West Indian Journal of Engineering for over 20 years, and there are many other examples of his service with respect to reviewing scholarly papers for these various journals. He's also served as external examiner for UTT's National Engineering Technician's Diploma in Mechanical Engineering for the last 6 years. And he has also served on several committees for the Trinidad and Tobago Bureau of Standards, Specifications Committee for Workplace Design, Indoor Air Quality, for example, Specifications Committee for Motor Vehicles Emissions, Building Code Project, Standards for Solar Water Heaters. He's a member of the Boiler Examiners Board. Some of us may not even know that such a thing exists, but he's served as a member and served on a committee for the certification of energy service companies for the Ministry of Energy. It's interesting. I know Professor Manohar has been here for many years, and I've been here also for many of those years as well. But the first time I met Professor Manohar was when he served as president of the Yoga Meditation Society of Trinidad and Tobago, and he was responsible for setting up a center about 3 miles from the village where I was born. And I first met him when he was president of the Yoga Meditation Center, and he served for more than 10 years. And he has served as a yoga instructor as well since 2004 for the UWI Sports Center, the Faculty of Engineering, as well as the Riverside Hindu School. And a lot of times, we see our colleagues here in the corridors, and we don't realize that the impact sometimes has a lot to do with what they do outside the university rather than inside. And he's been extremely impactful as a result of those kinds of contributions as well. Let me talk a little bit, though, about his distinguished research work. He does have a wonderful record, and during his career at UWI, he has published over 85 scholarly papers, including 43 referee journal papers, 15 conference papers, in fact, several more than that. And, he continues to be active in research, and I expect him to continue to do that even after retirement in many years to come. I want to close off by quoting from one of the assessors who reviewed his CV for promotion to professor, and he notes, Dr. Manohar works in the field of energy and thermal fuel sciences. Particularly noteworthy are the breadth of his contributions in areas ranging from thermal insulation to wave energy harnessing and wind power. I found his papers to be well-written and impactful in addressing the energy challenges that humanity faces. They present fundamental insights of much import to applications and contribute significantly to advancing the state of knowledge in the field. He has distinguished himself through his scholarly output in several peer-reviewed journals, and his research meets the high academic standard expected of faculty at his stage of the career. Colleagues, ladies and gentlemen, please join me in welcoming Professor Krishpersad Manohar to give his lecture on a journey to net zero insulation for sustainability. I thank you.
Good afternoon. Good afternoon, everyone. Front row, all protocols observed. So I think everybody knows the distinguished guests. So today, I'll be speaking on the topic, the journey to net zero, with specific reference to thermal insulation. Now, undoubtedly, the most pressing issue facing the survival of life on Earth today is the accelerated pace of global warming. And this, if not everybody, but most of you will know, is driven by the excessive amount of CO2 in the atmosphere. And the goal is to get to net zero by 2050. Are we on track? Slight technical difficulty. Are we on track for the lecture? It's not working here. Which one? Okay. All right. Thanks, Ganesh. Okay, so let's get back on track. So today I'll be looking at why this urgent need. What is this urgent need to get to net zero? And I'll be touching on what are the major contributors, because we need to know the root source of the problem before we can address it. And then I'll be looking at the impact of thermal insulation, specifically building thermal insulation on CO2 emissions, the direction of present research, and that might be a little surprising, and the future of building thermal insulation. So I think everyone is aware of this Paris Agreement in 2015. And at this Paris Agreement, it covered climate change mitigation, adaptation, and finance. And at this 2015 summit, goals were set to try and achieve net zero by 2050. More than 150 governments signed on to it, and Trinidad and Tobago was no exception. Trinidad and Tobago, the government pledged to reduce emissions by 15% relative to business as usual by 2030. Now, I must tell you, to date, no country has reached or is achieving what they pledged. A couple of minutes, you'll see where we are heading. So it's common knowledge that this issue is caused by the over-reliance on fossil fuel. You see, before the Industrial Revolution, the CO2 levels in the atmosphere was around 280 parts per million. Now, CO2 is very essential. It is essential for maintaining the atmosphere on Earth as we know it to sustain life. But like everything else, too much of something not good. And that is exactly what is happening. It's too much CO2. Now, CO2 is vital because that maintains the Earth's temperature to such a level that we humans can live in it comfortably. That greenhouse effect. So the CO2 is like a control valve, and it regulates how much radiation is leaving the Earth. But with the excessive amount of CO2 in the atmosphere, too much radiation is being retained, causing global warming. You see here, without CO2, the average Earth's temperature will be around minus 18 degrees C. Could you imagine living in that? And that is compared to what the Earth's average temperature now is around 14 degrees C because of CO2. So exactly where we are right now. So if you look at, I need the pointer, but I'll get it in a couple minutes. So where we are right now, you see on the diagram, way up in the graph, we are actually about 422 parts per million, 421 last year, and we are adding about 2 parts per million every year of CO2. And where we need to get is around 350 parts per million by the end of this century. And if we don't get there, what would happen is that it's going to trigger a tipping point that is going to be irreversible with respect to climate change. And that spells doom. Now, we know fossil fuel is a problem, but fossil fuel actually powers most aspects of modern life. In fact, fossil fuel is responsible for the lecture here. Yeah? So it is not like a switch that you can just turn off. Fossil fuel is the problem and you turn off the switch. No. We would all complain. That's for sure. So we got to look at how to get that line coming down. Let me see, is the pointer working? No, it's not working on the screen, so.
Yes. So if we look at this graph here, this is where we would like to get. Coming down to 2 degrees. That is 2 degrees above pre-industrialization time, right? Look at the line here, production implied by climate pledges. So that was done at the 2015 conference. But look the direction it's heading. But look at the red line on top. That is what is actually happening. So that scenario is really leading us down to a direction where it will be no return. We got to get that line coming down. Now, how can we do that?
in 2023, the global ocean was the warmest it has ever been. And to realize the downward trend that I'm talking about, we need something called deep decarbonization. So we hear a lot about reducing emissions, but reducing emissions alone cannot get that line sloping downwards. Reducing emissions, we want to achieve by 2015 a flat line, net zero. And then we have to start getting it down. And to achieve that, we need deep decarbonization. So to put in a little context, where are we heading? The 2.4 degree is the pledge. But where we're actually heading is the current policies. We're heading to 3 degrees. What does that mean in layman language? With a 3-degree increase, cities like Miami, Shanghai, Osaka, to name a few, and Port of Spain won't be spared if we hit the 3 degrees. So we need to understand what is causing the problem, and then we can address the problem. So to touch a little bit on who. So we all know China is the biggest contributor, right? We to be blamed also, because we want everything made in China because it's made cheap. So we're asking them to make it, yeah? So anyway, they're the biggest contributor, followed by the US, then by India. So I will not go down the list. But in the country, what is responsible for the CO2? You see, power, electricity. Electricity is needed for almost any facet of life. And in this chart here, you're seeing that more than 80% of the world's electricity is still being generated from fossil fuel. And the average carbon intensity for electricity is about 475 grams of CO2 for every kilowatt hour. So you can actually check your electricity bill and see how much CO2 you are responsible for emitting every kilowatt hour you use. Now, how is this electricity used? So if we go back to the big countries, if you look at the combined services sector and the residential sector, you would see that it is close to about 30-something percent, closing up to 40%. And this is in China. If we look at the US, and again you combine the commercial and residential, it's going to eclipse the biggest one, transportation. Similar trend. How about the next contributor? India. Again, you see the same pattern. The domestic and commercial sector, close up to 40%. How about small Trinidad? Any difference? Let's see. In 2020 report, Trinidad, the electricity consumption by the residential and commercial, 40%. So you see what is happening. Electricity generated by fossil fuel, more than 80%. And out of that, 40% is being used by the residential and commercial sector. Now, how is this distributed in your homes. Statistics here, I know this one is fine and difficult to highlight without the pointer. Hope to get it soon. But the top one there is the air conditioning. The next one, the second largest there, so I'm reading here from the screen, space heating, and you have water heating. And then if you go down the line a bit, you will see air handlers for cooling and air handlers for heating. Now, if you add up all that, it comes up to about 50% of the energy that you use in your homes. Yes, so we're back on track. So this data, again, from this study by the Arizona State University,
It shows that heating and cooling your homes accounts for 50% of the yearly energy cost. And they researched and came up with a known fact. Those of us who are in thermal engineering knew this fact, that with effective thermal insulation, you can reduce that heating and cooling bill. Now in Trinidad we have cooling, right? That heating and cooling bill by 50% with thermal insulation. So a scenario here in Trinidad. Here is cooling. In tropical countries, up to 60% of the heat load comes from the ceiling, the roof. Yeah? And if we look around the walls in this building, we won't see insulation like we'll see in say, North America. We have a nice ceiling, but this ceiling was designed to look good, not for insulation. You go on top of the ceiling, you will not see insulation. 60% of the heat gain. But it helps. A little bit of insulation do help. So, again, ASHRAE. ASHRAE is the leading organization in the world that deals with space conditioning. They write all the standards and so on when it comes to space conditioning. And note, approximately 40% of the CO2 generated in the world is linked to the built environment. So, insulation can reduce that heating and cooling load by up to 50%. And that, of course, translates into CO2 emissions. This here, I highlighted increased use. You see, in Trinidad, we don't have much information. So I have to use the information I have, and in North America, we do get a lot of information. So increased use. This work showed that 9 out of 10 buildings in the US is under-insulated. 9 out of 10. So that is why they're saying here, with the increased use, we can save up to about 43 million metric tons of CO2. Increased use. Okay? So, it sounds good. Insulation is savior. but that's half the story. What about the next side of the coin? You see, commercial insulation. These industries are very heavy consumers of energy. Fiberglass, and I'll be referring to fiberglass quite often because fiberglass is the most commonly used building thermal insulation, and 70% of the insulation used in buildings is fiberglass. So I'll be using that as the example because it's the most commonly used. So these industries consume a lot of energy. Let me show you some numbers. In 2019, the 23 fiberglass plants reported to the US Environmental Protection Agency. And look at the number. 1,213,287 million metric tons. And that represented 53%. So the number is actually twice that. So to get the fiberglass or to get the thermal insulation, this is the price that is being paid. This diagram showing the thermal insulations and their CO2 emissions. And it works out on the average for the commercially available insulation, about 8 kilograms of CO2 emissions is produced for every kilogram of product. This researcher, Lalantoy, in 2020, worked on the carbon payback time. So we have to stop talking about dollars and cents and start talking about carbon if we need to save ourselves. What is the carbon payback time? And the research showed that for fiberglass, it takes about 7 years to pay back. So to get the fiberglass, here, we're emitting CO2, but when we use the fiberglass, we're saving energy. So the energy saved takes about 7 years to reach net zero. So that's the price. Coming back to the diagram you saw before, we need to get the line sloping down. This here, the production gap need to get smaller. And what we need is deep decarbonizing. So deep decarbonizing would involve creating carbon sink. And when you sink the carbon or remove it from the atmosphere, you have to store it somewhere. So you have to sequester the carbon. And we have to continue working on reducing energy consumption, thereby reducing emissions. So the combination of this would start bringing it to net zero, and after 2050, the line will start sloping downwards. That's the direction. Remember, we cannot just turn the switch and stop using fossil fuel. So it is noted here by the International Energy Agency. To get there, 75% of the emission reduction necessary to meet net zero is dependent on technologies that have not yet reached commercial maturity. So this is present-day research that people are doing from all directions in all different fields to try and get to net zero, because it's everybody's business. Now,
where can we look for solutions? So the question, what is the biggest carbon sink in the world? The ocean. After that, the forest. Well, what's left of it, because we depleting the forest also. The forest absorbs about 2.6 billion tons of carbon dioxide every year. So researchers are looking towards nature for the answer. So the question, can we have an ideal thermal insulation? What if we got a thermal insulator and the material is readily available, inexpensive? So, by the way, one of the reasons why 9 out of 10 homes are under-insulated, one of the reasons is expensive. The insulation is expensive. So, if we have something that is inexpensive, and it's natural fibers, and it's also a heavily carbon negative, economically viable, in abundant supply, and environmentally friendly. Now, I will not be touching on environmentally friendly, but that is another big issue. Hundreds of thousands of tons of insulating materials from the retrofitting of buildings are being dumped every day, and that is wreaking havoc in the environment. But not going there in this lecture. But the material should be environmentally friendly. So researchers turn to what? Straw. They look towards nature for the solution, and straw.
So in 2023, this article, there are now straw bale homes in over 50 countries and in every US state. But how practical is that? Could we put a bale of straw on the wall? Nobody would want that, yeah? Bale of straw, that thick? Not really practical. So researchers now, seeing that that is not really feasible, started to make panels. So the panels here, and they're insulating the panels with straw. So these are the panels that you will have in the walls. In the UK, the School of Natural Building, they announced
the publication of an environmental product declaration, an EPD, for straw as an insulator. So it's officially an insulating material in the UK. Here at the University of Bath, you're seeing Professor Walker and Dr. Platt, and Dr. Platt pressing down his straw while making the straw panel. So the focus on straw in these countries was really because of availability. Building your house with straw, reminded of anything? Three Little Pigs? Got to make sure you have no wolf around there, huh? That's for sure. Now, what do we see with the straw? In the formation stage, to form the straw, you have plants, right? So that is a carbon sink. And when you sink that carbon, it forms the material, the straw. And it's sequestered or stored in the material. And when you use the material, what is happening? You're saving energy. So it has the three key ingredients: sink, sequestration, and reduction. Three ingredients for deep decarbonizing. But you see, a fibrous thermal insulation is not just taking some straw and packing it. It's much more than that. When you buy a piece of fiberglass, for example, that product is scientifically developed and skillfully engineered. It may not look so, but it is. The apparent thermal conductivity of that material that you'll see coated on it is really a complex combination of three modes of heat transfer: conduction, convection, and radiation. So to be an effective fibrous thermal insulation, you must have certain properties. Now, this one is pretty fine, so I'll read it out. The apparent thermal conductivity for building thermal insulation, so it's building thermal insulation we're talking about, has to be in the range between 0.3 to 0.7 watt per meter Kelvin. The arrangement of that fibers, it's supposed to reduce thermal radiation and block natural convection. So density comes in the picture. The material should not settle under gravity. So remember, Dr. Platt pushing down the straw. You don't want to put the straw in the wall and then it settles down. So it should not settle under gravity. And when you look at the characteristics of it, it should give you a hook-shaped graph of thermal conductivity versus density. So at UWI, we set out to see if we can get something that could satisfy most of those criteria that was outlined for an ideal building thermal insulation. So, the optimum density should not be excessively high, because remember, you're putting this in the wall and it will contribute to the weight of the building. The material should not pose any health risk. And we live in a very high humidity environment. So the material should be a little bit moisture tolerant. These are the conditions we set here on campus, a little more than what was outlined. The environmental part, at the disposal stage, we're looking for something biodegradable, environmental friendly. It should have sequestrated carbon. And the cradle-to-gate analysis, that should be a net carbon sink. Can we find such a material? So, looking at thermal insulation, I compare it here with fiberglass. And since we're looking at natural fibers, and I said the straw was used because of availability. In Trinidad here, what was available at that time was coconut fiber and sugarcane fiber. Now, when you look at the numbers here, the fiberglass is about 20 microns max. And the coconut fiber average about 267, and the sugarcane fiber about 313. So that is considered large diameter. Now when you go back to the science, you have models to predict the thermal conductivity of the fibrous materials. But all these models were developed for small diameter fibers. And they weren't applicable for the large diameter fibers. So we had to step back a bit and now develop a model that will be applicable for the large diameter fibers. So a model was done. I'm not going into the nitty-gritty of the model, don't get too worried. I'll just give you the results. So the radiation part. Remember, it's a complex combination of 3 modes of heat transfer. The radiation model, and from that, this equation was developed. Then, the conduction part, some models were developed, and the equations derived from those models were here. And the air contribution model was developed, and these are the equations. Right? So the results then. When we used the fiber diameter for coconut fiber at a temperature of 20 degrees C, look at the results. So you're seeing the solid conduction, radiation, air conduction. When combined, you're seeing the sort of hook-shaped graph. Similar when we use the fiber diameter for sugarcane fiber. Now, note, the thermal conductivity is within the range. It's pretty small, but around 0.05, within the range for use as building thermal insulation. And to be a building thermal insulation, thermal conductivity is one of the most critical parameter. So seeing that the model predicted that, hey, yes, there is something in these fibers that we can use, it paved the way now for the engineering investigation. So we got some coconut fiber. So the coir here, extracted from the husk, and we got some sugarcane fiber. And these were now tested. Remember, we don't want the insulation settling. So the first investigation we had to do was to see what is the density above which the fiber will not settle under gravity, under its own weight. And that we found to be, for the coconut fiber, 40 kilograms per meter cube. And for the sugarcane fiber, 70 kilograms per meter cube. So now we can go ahead and test above these. Okay? Makes no sense testing lower. So tests were conducted, and specimens 25.4, 38, and 50.4, or what we are accustomed in 1 inch, inch and a half, 2 inch specimens were tested. And the equipment was a Fox 304, laser comp Fox. This apparatus operates under the ASTM C518, and don't worry too much about the numbers. It is the standard for testing building thermal insulation. Calibrated with a standard reference material, and it was designed to test material within the range of 0.005 to 0.35 watt per meter Kelvin, which covers the range of building thermal insulation. Now, these tests are very costly and very time consuming. It takes between 4 to 6 hours to get one test. And you're talking about hundreds of tests. Right? You can't do ripe mango picking. You have to do many tests, repeated, same conditions. So that's why we had to do the science investigation first. But what do we see? hook-shaped graph, coconut fiber. Hook-shaped graph, sugarcane fiber. And the results show for the coconut fiber at the optimum density is about 0.048 watt per meter Kelvin, and for the sugarcane fiber about 0.046 watt per meter Kelvin. The coconut fiber optimum density is around 70 kilograms per meter cube, and I rounded off that other one, about 100 kilograms per meter cube. Just some actual results here for the 50.4 millimeter thick for the coconut fiber and for the sugarcane fiber. Now, so far, it looks promising. But remember, we're looking to substitute this insulation for fiberglass. So how does this compare to fiberglass? Is it possible to substitute it? Fiberglass usually comes in batt or roll, if you want to call it. We call it fiberglass batt in this field of study. And 4-inch thick is very common. So I have just chosen this one. You will have similar results if you choose different size to compare. So I just chose this one for comparison. So a 4-inch thick fiberglass batt. And again, the reason because fiberglass is 70% of the insulation. And we would like to get Energy Star recommended thermal insulation. So these are the Energy Star recommended thermal insulation values for the US. And again, 9 out of 10 homes are not meeting this. That's why they have, issues with their energy bill. So Energy Star rated, it is recommended. 4-inch thick wall, it should be between the range of R13 to R15. So for comparison, let's see how well sugarcane fiber and coconut fiber compares. So if we got Energy Star recommended insulation,
R15, 100 millimeter thick, or 4-inch thick wall, and we're considering a 1 meter square. So for the fiberglass, 100 millimeters, thermal conductivity 0.038, and fiberglass vary in density. But for the batt that we're considering, this here is about the common density, 22.6 kilogram per meter cube. So for a 1 meter square piece of insulation, what you're going to have, a mass of about 2.26 kilogram. That amount of fiberglass, to get that amount, it will cost you carbon money, 5 kilograms of CO2. And it will take you about 7 years for it to repay. So we're using the same size, 1 meter square, but now with coconut fiber. What do you see? The insulation is going to be a little thicker than 100 millimeters, 127 millimeters, so about an inch more thicker. And that is expected because the thermal conductivity is a little higher, but not much thicker, 1 inch more on your wall. But look at the benefits for putting 1 inch more on your wall. Sequestrated carbon about 3 times. So, similar for the sugarcane fiber, the sequestrated carbon about 4 times what you're actually spending. And just for about 21 millimeters more.
here you see for the R13, so we come to the lower side of the Energy Star rating. The thickness comes a little better. Instead of 127, if you want a R13 rating, it works out to 110 millimeters. So 10 millimeters more on your wall, and you have sequestrated carbon instead of carbon emissions. Sugarcane fiber, 5 millimeters more on your wall. So what you are seeing here, you can get Energy Star rated thermal insulation or Energy Star recommended thermal insulation values for very close, similar thickness to the commercial insulation. So the natural fibers has sequestrated carbon, and the sequestrated carbon is significant. When in use, the carbon payback time for the natural fibers is 0, whereas the carbon payback time for the fiberglass, 7 years. The only disadvantage I see is the weight. But when we're talking about a building and the structure, the weight, and that need to be investigated further, is not significant in my opinion when you're talking about a structure of a building. So instead of 2.2 kilograms, you have, say, max 10 kilograms in that space. So it is a disadvantage, the weight. Now, the insulation material comes in different forms. So you saw the picture with the fiberglass bat.
So if we're going to replace fiberglass, then we must have something similar to fiberglass. Yeah? So can we make insulation bats? So with coconut fiber, yes. You all have your orchid plant pots, right? Yeah? Coconut fiber weaved together. And it's flexible. So we made insulation bats with coconut fiber that can replicate the fiberglass insulation bat. The next form that it comes in is rigid. So you have rigid panels that are made, the sizes are standard. Can we make rigid panels? So with the sugarcane fiber, we made some rigid panels. This here is a ceiling tile. Yeah? And this ceiling tile has been in my office for more than 15 years. This picture was taken last Friday. And it showed very little. We weren't able, Dr. Adianjo and I, we were examining it, and we weren't seeing any kind of deterioration in it after more than 15 years. And this tile was made with cornstarch. Yeah? Went across UWI Grocery and bought cornstarch. And we made that tile. Still in my office. So, giving you an idea of can the material last? So far, it's holding up. Biodegradable, cornstarch, sugarcane fiber. And the other form that the insulation come in is loose fill. So the loose fill material that they will just blow in the ceiling to fill spaces hard to reach. And the sugarcane fiber can be used as loose fill. So we can replicate the 3 ways in which the insulation come. Flexible bat, rigid panel, and loose fill. So it's showing potential that it is capable of replacing these high CO2 emission insulations that we have. So I will now just wrap up a bit and look at the carbon sink. So what happens is that the plants, the plants with photosynthesis, they absorb the carbon and they change it into biomass. 50% of that dry biomass is carbon. And when we look at the CO2 having that atomic number of 44, so for every kilogram of biomass, half of it is carbon. And for every kilogram of carbon, we have sequestrated or sink from the atmosphere 3.67 kilograms of CO2. How does that work out in terms of numbers? So this research was done in Australia, the CSIRO report 2022, and it showed that the coconut trees can provide 51.14 tons per hectare per year. That is of the material, the biomass material. And when you convert that into CO2 that is as sequestrated from the air, it works out to about 188.6 tons of CO2 per hectare per year. Sugarcane fiber, similar. This research was done in Sao Paulo, and it's showing that when you crunch the numbers, approximately 107 tons of CO2 per hectare per year. The coconut trees behave like a forest. What does that mean? If we can reach the stage where we substitute natural fibers for the higher energy fiberglass. This Fredonia group in 2020, they did a forecast for the amount of fiberglass you will need in 2024. And they forecasted you will need 5.6 million metric tons. Imagine how much CO2 emissions is that. If we substitute that with natural fibers, it will come down to about 41 million metric tons of CO2 that we'll be removing from the atmosphere. We're not talking about the savings that you will get by the reduced energy consumption. We're just talking about the material itself. Only the material. 41 million metric tons. The production of 1 ton of fiberglass emits about 2.2 to 2.5 tons of CO2. So those were the numbers that was used to do the figures that was shown before. Coconut fiber and sugarcane fiber, it's negative. So the little diagram here, are we going back to the atmosphere? No, they're being sequestrated, right, with the plants. So where have we reached? Remember, this is research that is developing. So, carbon sink, yes. Sequestration, yes. Emission reduction, yes, because the insulation saves energy. Heavily carbon negative, remember these were some of the things we were looking for in an ideal insulator. Heavily carbon negative, yes. Environmentally friendly, yes. Prototypes built, Yes. Now, to be on the commercial market is still a long way to go. And I was discussing with my dean here. Big fish will eat you up, right? Yeah. So it's still a long way to go. We have to look at the economics of it. Abundant supply, I did some preliminary checks. It is possible to get about 7 million tons of coir, but that is not enough. We need about 30 million tons to replace fiberglass. I'm talking about worldwide. But surprising, well, coir has other uses, right? You know about your straw mat, you know about your orchid pot, and so on. People still want that, right? So you can't cut out those industry. You can't kill those. Sugarcane fiber has very little use. It is looked at as a kind of nuisance in terms of waste material. And from the preliminary research, worldwide, it is more than 500 million tons of sugarcane fiber that has very little use. So, is it abundant? Question mark. It seems so. Health and safety, very important if you're going commercial with anything. That's why I say we still have a long way to go. Health and safety and fire safety, very critical. So some of these things we're working on. So, towards commercial maturity, remember, about 75% to get to net zero still depends on things that are not commercially matured as yet. So we're heading there. Sustainable. So technology being developed is focused on sustainable natural fibers for building insulation, carbon sink when you're producing it. Note, very important, it should have thermal insulating properties comparable to the commercial one that we're looking to replace. It must be comparable. And provide the equivalent Energy Star recommended R values. Not only provide it, but it should be of a comparable thickness. Very important, because the bale of straw that is about 36 inches thick gives you an R value of 30, right? But you can get an R value of 30 with this if you properly engineer it. Scientifically developed, skillfully engineered. See? That's the difference. So in conclusion, the built environment contributes about 40% towards global CO2 emissions, of which 50% is attributed to space conditioning. Space conditioning, our nice air-conditioned environment here. Effective building thermal insulation can reduce that energy consumption for space conditioning by 50%. On this journey to net zero, we're looking for deep decarbonization. That is the only way, the only realistic way we can get that line sloping down. And for that, we need CO2 emission reduction, sequestration of carbon, and carbon sink. And the natural fibers has those qualities or properties to give carbon sink in the plants, sequestrated carbon in the fibers, and when you're using it, effective thermal insulation, reducing the CO2 emissions. So with that, I want to say thank you all very much for your attention.
Good evening, everybody. I'm Dr. Farnan from the Optometry Unit in the Faculty of Medical Sciences. All protocols observed. Prof, that was a very enjoyable and thought-provoking lectures. So we have many questions. Let's put up our hands and ask Prof all those questions you have in your mind. I'm sure you have many. Don't be shy. Great. The Deputy Principal. The Deputy Principal has a question here.
Thank you very much, Professor Manohar. In fact, I'm really happy I attended this lecture. In fact, I attend all lectures because I was really curious to hear what you had to say. And I know you have focused on building insulation, looking at possible replacements for fiberglass. But I'm also wondering whether the design of buildings have a very important part to play in all of this. I remember in the old days, buildings were designed differently. High ceilings, large windows that made use of natural lighting, natural ventilation. But over the last probably couple of decades, our buildings, and I'm talking about the tropics, we tend to build boxes, and then we have to air condition these buildings. And the campus is no exception to this. In fact, my office and some of the older offices, like principal's office, the floors are wooden, so they are elevated, high ceilings, big windows. And in fact, when I moved into my office several years ago, I used to open the windows and get that natural ventilation. And my house is the same. I don't use air conditioning in my house because it's an old house, probably about 120 years old. So there are large windows, high ceilings, wooden floor, and I'm comfortable with it. So I'm wondering whether that is also part of the problem, that we are designing buildings unsuitable for the tropics. And because I'm also chair of our campus environmental committee, I'm really concerned about this, that we are creating problems for ourselves, and now we have to look at other other strategies to keep the areas cool when we could have just designed and build these structures differently. Thank you.
Yes, Prof, you are correct. And in fact, this is the direction that the architects are taking now. In the tropical regions, we don't use much air conditioning, and the architects are going back to that kind of design because of global warming. So it is, as one colleague was telling me when I told him about the straw, it is like making a 360-degree turn and coming back to building design. So yes, the architects are looking into that matter, and it is something that is also another facet on the journey to net zero, the design of buildings. Yeah. But in the temperate countries, insulation is a must. And that's why you see me focusing and giving data for North America and these areas. Because in the tropical regions, insulation, and we know it in Trinidad, our buildings don't have, right? And you're correct. It is the design, the follow fashion of the buildings that in the other regions, we patterned our tropical region in that, ending up in problems. But we are going back to it. Yes.
Great. So there's a gentleman in the back there. Thank you, sir.
Hi. Excellent presentation, Prof, and congratulations. And I'm so happy to hear that, you have used the materials from the agriculture. And since, I'm from the Faculty of Food and Agriculture, I'm happy to see, and also it opened up a lot of avenues and opportunities for using the fibers from the agricultural field. So in that case, what I would like to know, what is the feasibility of using banana fiber or the bamboo fiber and also other fibers from the agriculture for this type of work, as well as even to the concrete blocks, right? So that is one thing. And also, I would like to know, with respect to the region here, and have you tested any other materials from the agricultural field? Because when it comes to the sugarcane, long back, the region would have grown a lot of sugarcane as well. And of course, we would have known that after cutting the canes, and they would have used to fire the whole field, then again, that is contributing to the emission of all sorts of gases, and also is environmental pollution. So this is a very innovative research, but I would like to know whether you have tested the fibers from banana as well as from bamboo. Thank you.
Yes, thank you very much, Prof, for that question. So yes, I tested banana fiber. And banana fiber showed to have similar thermal insulating properties, and the optimum density was actually lower than that of sugarcane fiber and coconut fiber. The banana fiber optimum density was around 40 kilograms per meter cube. And the reason for that, it's because it's a finer fiber. You see, the finer the fiber, it influences the surface area, and that influences the heat transfer mechanisms. And this is why you will find that the fiberglass optimum density is around 22, and we have some of the finer fiberglass that optimum density is around 10 and 15. So the answer, did we test? Yes, I tested fiberglass. Not fiberglass. I tested the banana fiber, and then company from one of these eastern countries, I think it's Korea or so. I stand corrected on the country, but they grow a lot of oil palm, and they shipped down about 5 bags of oil palm fiber for me, and I tested oil palm fiber also. But with the banana fiber, it was very difficult to extract the fiber. That was my experience with the banana fiber. So banana fiber is better, yes, but extraction and getting the fiber was more difficult. Yeah?
Thank you. We have another question there from a gentleman.
Hi. With regards to the, I see you still have to explore the health and safety aspects and the fire and the flammability stuff. Do you foresee, if it doesn't meet the standards, would you add any additives to compensate for that? And if so, how would that affect the carbon footprint or the payback period? Or is there any, or is it the possibility of a compromise between using fiberglass and baking in some of the organic materials like the coconut fiber or the bagasse on the table, or potential option?
Adding the fire retardants has already been checked with the straw. So I don't foresee any complications. And also, some of these fire retardants serve as insect repellents. So there you're having 2 aspects to consider being addressed by one material. The idea of mixing the fibers will severely impact the optimum density. And remember, I mentioned that the density of the material affects the weight, and this goes on the structure. And also that is another aspect that has to be looked at. So testing has already been done with respect to the fire retardants, health and safety. Fiberglass is one of the most, how to put it, you have a whole lot of issues with fiberglass. In fact, those of you who looked at the program on television, Prof, that was the question that the interviewer asked. We have all these issues with fiberglass, and they're recommending to move away from fiberglass. And that was before we spoke about we moving away from the fiberglass. He thought I was suggesting to go back. So fiberglass, we have a lot of issues with health and safety, which we will not have with the larger diameter fibers. Yeah? But again, all these things need to be further investigated. Yeah?
Great. I think we have another question from our colleague up back there.
Thank you very much for that very informative lecture. I noticed that no matter what we do, there will be some amount of carbon dioxide emission. Is there a possibility, I mean, you have strengthened the use of insulation to prevent the actual production of carbon dioxide. What about if we take the carbon dioxide that is produced in the condensers and transform it? Is there some method we could use, since that is always inevitable, that we could transform the carbon dioxide that is released from the condensers into some product which is not as or less user-friendly than the carbon dioxide emission? Could we produce some, they say carbon could make diamond. I'm not saying that would happen, but transform it into something better that wouldn't cause global warming. Thank you very much.
Okay, so a lot of research is being done in extracting the carbon, and in fact there are billions of dollars in funding for these carbon projects. A paper published by the US Energy Department in December 2023 showed 13 out of 15 projects that they funded failed. And the other two was not showing any promise. And the reason being, this CO2 that they're trying to extract from the atmosphere, the energy that they were using to do it, the process of converting that carbon to something else, they were trying to sequester the carbon and store it and pump it in the ground and all these things. And they're getting real funding. Huh? You go with a carbon reducing project and you're going to get plenty money. That's a fact. But it all showed that in the process, they were producing more carbon than they were extracting to convert it into something else. And if we look at the fact, we're talking about 420 parts per million in the atmosphere. What percentage that works out to? 0.04%. So you're trying to get something that is 0.04% of this atmosphere out. So realistically, the energy you're going to use to get that 0.0% out is going to be more than how much you're really taking out, in terms of carbon we're talking about. So that is a difficulty that we are being faced. And remember, these technologies, what you're saying, people are researching as we speak and still developing. And who knows, tomorrow somebody might come up with something that will be effective. So that kind of research is being done, but so far it has not given positive results. Yeah?
Great, thank you for that question. Any more questions for Prof? Yes, one more question there.
Hi, Gadesh. So you said how long it will take to commercialize this? I think it was something like 15 years, I said.
Yes, the TV guy asked that.
Yeah. But what is the main challenge in terms of commercializing? No, because I'm looking at it from a net zero standpoint, and we're supposed to reduce by 50% by 2030, and then net zero by 2050, right? We're nowhere close to that, right?
Correct.
But so what I'm saying is that we have a lot of these technologies that coming out as offering these things, and it's giving people the impression that we're making progress towards doing things. And it's all a way for us to continue the life that we live in without making the rapid changes that we need to be making in order to really reach the our net zero pledges. But if I was to take and believe for a moment that, okay, these technological changes is going to improve, what would it take for you to commercialize this faster? Because even after we commercialize, we still have to retrofit, we still have to, all those things are years. We reached 2050 long, I mean, you still haven't reached any further. So, but what would it take to actually accelerate these types of innovations?
Okay, well, one is funding. 2, buy-in. We got to get the big players in the industry to buy in. And we have to do all the market research and so on. And most of these things are now beyond, say, the engineering researcher. So to commercialize this, we would need to set up a multidisciplinary team and then move ahead with that. In terms of time, I can't say. All I can say is we're going to try to move as fast as possible, as I was discussing with Dean here also. With his full support, he promised. But Trinidad is a small place. And if you go to step on the toes of the big players, you're going to be in trouble. So the next step, this is just my thinking, the next step I'm thinking is to try and get the big fish to buy in. Because if you're going to say you're coming up with something to replace fiberglass, that is a multi-billion-dollar industry. They're going to crush you. So to go to commercialization, very important step in my opinion, is to get the big companies to buy into this product and then to start doing all the other steps to get it to commercial standard. And that is a lot of work as yet. In fact, I think from this stage where the science and engineering has reached, from science and engineering to get to a product on the shelf is a much larger step. Time-wise, I honestly can't say.
Great. So thank you, everybody, for those wonderful questions, and I'll hand back to the chair. Thank you, Bob.
All right, so thank you very much, Dr. Farnan. He's one of our dynamic committee members on the Open Lectures Committee, as you can tell from Faculty of Medical Sciences. At this point, I'd like to call on the Deputy Principal, Professor Indar Ramnarayan, to make a presentation to our esteemed professor. All right, folks, this brings us to the end of a really thought-provoking and I will say very inspiring evening of intellectual engagement, and I will certainly say of hope. And what I really found wonderful about Professor's talk was that it's local materials. It tells you the potential. Who knows if this thing takes off, where it could put Trinidad and Tobago economically. All right, so with that, our heartfelt thanks to our speaker for the evening, Professor Krishpersad Manohar. Thank you for sharing your highly successful journey through academia with us. We really have been truly inspired. Thank you also to none other than Deputy Principal, Professor Indar Ramnarine. Thank you for your support always and forever to the Open Lectures Committee and the UWI and intellectual engagement. You did say you attend all professorial lectures, excellent. And Dean of the Faculty of Engineering, Professor Bisham Ramlal, your leadership and caring has been making all the difference. We've been watching. Thank you, sir. And of course, none of this could have been possible without the folks working diligently behind the scene, marketing and communications. Thank you for all your hard work under the expert guidance of Ms. Chanel Glasgow and the support of Ms. Jamila Frank and all the wonderful people that they're working with. Special thanks also to the staff of Division of Facilities Management, staff of the Learning Resource Center, where we all are sitting right now, the campus security who have us feeling safe, and the members of the media, of course. And last but not least, you, my dear audience, for your curiosity and engagement. For that, I thank you and love you all for your intrigue and interest in how to make the world a better place and intellectual stimulation. And with that, folks, I bid you good night and farewell, but not without saying, do join us for some light refreshments, and it's a wrap. Thank you. Good night.